Okay, it doesn't. Okay, so well, so Jair is an expert in color-rush condensate computations, and he did his PhD in sorry. In Ben Gurion, and he has been working in Saclay and Givascula, and he is going to tell us about next to in order Dijet production in proton-nucleon collisions.
Hey, thank you, Miguel.
Okay.
So this is a work which I'm doing together with Edmond Janku. And we plan to publish 4 papers on this matter. 2 of them already been published, and we hope to publish another 2 papers soon. I'm going to tell you about the 2 papers first, and then I will give you a quick idea what are the next steps that we are going to take. So, as Miguel mentioned, we are interested to compute the Dijet production in proton-nucleus collisions. And this we are doing it in the forward regime. You can see, for example, the typical situation that we are dealing with at the bottom of the slide. So we have a proton colliding with some nucleus. And we assume that most of the energy of the proton is concentrated in one of the constituent quarks. And this quark, with the evolution in time, can somehow emit a gluon. And the gluon and the remaining quark can interact with the target nucleus. And then they get some color rotation, and when they come out, they can produce 2 Dijets. So the situation in leading order, you see it here, and this was computed by Cyril Marquet. I'm going to show you a new way to rederive this result, and then I will show you how to generalize it for higher orders. So before we continue, I will just comment that we are computing the kinematics precisely, which means that we are not going to assume anything about that. Everything will be done as it should. And the scattering process, we assume that the target nucleus consists of some dense bunch of partons, and it will be described equally, which means that we attach Wilson lines to the partons which are passing through the target. So now let me describe you the formalism that we are working with. So this is known as the outgoing state formalism, which means that we are interested to find a state which encodes all the information about the process, both the time evolution and the interaction between the projectile and the target. So if we were just interested to know what is the time evolution of an incoming quantum state, we know how to do that. This is very simple. We just have to act with the unitary time operator, which is dictated by the Schrödinger equation. And this is the following unitary operator, which you can see here. Now, this state doesn't know anything, of course, about the interaction between the projectile and the target. If we want to have a state which know about the interaction, we have to act with 3 operators. You can see the definition of this state here. This is what we call the outgoing state. Once we have this state, we can find any expectation values directly by the relation that you can find at the bottom of the slide. So we just have to plug inside the operator that we are interested to find its expectation value, and then we have any interesting physical observable cross section or whatever you want. Let's see more precisely how to get the result for the leading order Dijet production cross-section. So the outgoing state, if we just expand the unitary time evolution operator up to order G, we just have 1 plus some term of order G. We expand the unitary time evolution operator from the two sides. That's how we generate the following two terms. And if we compute these terms, so we insert the two relevant matrix elements which are involved in each of the terms, and the what you see here is the energy denominator. Once we plug it inside, we will find the following result. Now, this result might look a little bit complicated when you first look at it, but this is actually a very well-constrained result. So there is nothing else that we can actually write. And let me tell you the reason why it is like that. So you see some blocks in some colors that I gave them, and I will give you some comments about that. So first is the overall prefactor. We know that this state is, of course, of order G, and the square root of Q is just something that have to make the dimensions right. Then we have some numerical coefficient, which I can explain to you later. And then we have some structure that you see in the yellow box. This is what will reproduce DGLAP structures. The block in green is the Weizsäcker-Williams field. Then comes the block in brown. This is the delta function, which give us the condition of the center of mass conservation. Then there is another block in red, which encodes the information of the scattering process. So you see that we have two terms. So each of these terms is the terms which are involved in this line. So the term which involved a scattering operator in between two quarks, this matrix element will give us only a Wilson line in the fundamental. That's why you see this V here. And the Wilson lines, the matrix element here will give us two Wilson lines, one in the fundamental representation, while the other one is in the adjoint representation because of the gluon that now it acts on. Okay, once we have this state, we can compute the cross sections, and we are doing it by plugging it inside the following definition of the cross section. So as we just saw, the leading order cross section is a cross section which comes from initial quark and initial gluon, which initiated the jet process. And once we plug inside the result for the outgoing state, we saw it in the previous slide, and we act upon this state with the number density operators, which are defined in the following way, we reproduce the same result that Cyril found in its calculations. So what we see is that indeed this result involved the DGLAP splitting function, some delta function for the conservation of energy, some Weizsäcker-Williams field that you see in this green box. And there is this blue box, which comes because of the Fourier transform. Another part of the result is the red box, which encodes the Wilson lines combinations. And it will be a good thing to remember that the structure that we get is some interaction between quadruple dipole, dipole, which is this term, another dipole, and just one dipole. So actually there is a general statement that even the higher orders cross section will involve only these two objects. So only the quadrupole and the dipole. And how these objects are actually defined. So they are defined by the following way. So these are their definition is a combination of 2 Wilson lines and combination of 4 Wilson lines. So the 4 terms which are involved in the leading order result, they actually, each one of them correspond to a diagram. And there is this slide, you can see one example of the diagrams which are involved as one of the terms. So for example, the term which included by this product of 2 dipoles is corresponding to the case here that we have a shock wave in the amplitude on the quark and the gluon, while on the conjugate amplitude, we have a shock wave acting only on the quark. Once we have this cross section, we can of course convolute it with a PDF. So, and then we make the transition from the partonic cross section to the Dijet cross section. This is given by the following relation. And we can even do another transition. So instead of having a Dijet, we can actually look for the cross section for measuring hadrons. And the relation between this partonic cross-section and the hadronic cross-section is given by the following relation here. So what you can see is that we have to integrate not only with a PDF, but also with fragmentation functions. Okay, so now we can look for the Trijet setup. So for the Trijet, first of all, maybe I should give you some words. Why is this interesting? So this was actually the matter of the first paper which I published with Edmond, and our aim, our interest was to compute the NLO Dijet production. But to compute the NLO Dijet production is actually quite a challenging thing, so it's not so easy to get this. And we thought to ourselves that the best way to start is to compute the real part of the NLO Dijet. And in order to do that, what we have to do is to compute the Trijet setup and then to integrate over one of the partons. So integration over one of the partons is equivalent to the situation that we are not measuring the parton. So let us see what is included in the Trijet setup. So a typical contribution is shown at the bottom of the slide. And again, we have a proton colliding with some nucleus, and one of the constituent quarks of the incoming proton is assumed to be to have most of the energy and to evolve with time. So in the leading order, we had, as you remember, just one gluon emitted, and now we allow one more step in the time evolution. So this gluon can actually split into 2 other gluons. So this is what is known as the triple gluon vertex. But of course, this is not the only thing that might happen. For example, we can just emit one more gluon from the incoming quark. So we have to take into account all these contributions. So, and of course, there is one more contribution that the instead of emitting 2 gluons, we can emit a quark anti-quark. So we have to compute these. First of all, we have to compute the outgoing state, and some typical diagrams for this case are shown in this slide here. I just want to give you another comment that we are using the light cone gauge. So these are not the all the diagrams which are involved, because in this gauge we have some peculiar thing which is known as the instantaneous the instantaneous vertex, which means that we can produce partons not like one after the other, but also directly. So we have a matrix element which connects between a quark to a case of a quark together with two gluons. These are not shown in this slide, but it's just good to know that they are exist, and we also computed them. Now, once we have the outgoing state for these diagrams, we can repeat the same procedure that we did for leading order. So we can compute the cross section for trijet production. So we take this trijet outgoing state, we plug it inside and act with the three number density operators on it. And then we have the result for the partonic cross sections for the case of two quarks together with anti-quark and a quark together with two gluons. And once we have these results, which I'm going to show you more explicitly in the next slide, we can convolute them with a PDF and find the trijet cross section. Then, as I'm going to discuss later on in my talk, we can integrate over one of the partons and make a transition from the trijet to the case of real NLO Dijet. So let me show you more explicitly how the results look like for the case of trijet. So now we don't have so the order of this result is of order alpha s square. We have some prefactors which are coming from the NC and NF. We have some dimensionful Q plus, which makes the dimensions right. We have some delta function. We have some exponent which comes from the Fourier transform. We have in the green box some bunch of Wilson lines. In the blue box, we have what is known as the kernel. This part will encode the time evolution of the scattering of the process. And in the red box, we have some combination of Wilson lines. This is shown here. So again, you can see that we have quadrupole and dipoles, and that is enough to write down the full result at large NC. And we have in gray box some subtraction terms. And these are the terms which will generate the different possibilities of the action of the shock wave. So the first term that you can see here, this is the term which corresponds to the situation that the shock wave is acting on the final state. So it's acting here and it is acting on the other side. So both on the amplitude and the conjugate amplitude, the shock wave appears on the quark, anti-quark, so at the end. And once we are subtracting some limits, so the first limit is the limit, for example, that Z and Z prime are going to the center of their mass. So Y is the position of the gluon, which is the same as the position of the center of the mass of the quark, anti-quark. Now, the situation that the shock wave acts on the gluon instead of on the final state, on the quark gluon instead of the final state, this corresponds to this limit. So this diagram is corresponding to the first limit. But of course, we have an identical diagram, which is like image diagram that the shock wave on the other side, on the conjugate amplitude is now acting on the quark gluon. So this is included in this subtraction term. And the situation that the shock wave acts on the quark gluon on the both side, this is included in the last subtraction term. So our initial approach to write down the Trijet cross section was to write down explicitly those terms, and this was not really elegant. So we could not use it so efficiently. And as I'm going to tell you in the next slide, there are some divergences. And by writing it in this compact way, we can actually trace them and get rid of them effectively. And there is also, of course, another symmetric term which is included in this result. This is due to the fact that we have two quarks. So we have to include symmetric term, which comes from the fact that the number density operator can be switched. So that's why you see this purple box here. Maybe let me give you some comment about this kernel. So as I mentioned, the kernel is what encodes the time evolution. And what you can see here, this capital phi, is what is known as the effective vertex. This vertex takes into account, so it knows this will reproduce the DGLAP splitting functions, and it knows both about the regular emission and the instantaneous emission. So that's about the kernel. Now, as I just said, this result contains many divergences. So we want to have a result at the end which is finite. So it's good to keep in mind what are the divergences that we want to get rid of. So in our computation, there will be involved 4 kinds of divergences. First one is the short distance poles, and these are some divergences which occur when 2 partons are approaching the location of each other. And another divergence is the soft divergence. This will occur when one parton is soft, which means the K plus, the longitudinal momentum, yes, is going to 0. Another divergence is the collinear, which means that this is the situation that 2 partons are having momentum which is parallel to each other. Or in position space, this means that partons are emitted far away from each other. We are going to explore these limits, and this collinear limit will be associated with some DGLAP evolution of the incoming PDF and the outgoing fragmentation functions. The 4th kind of divergence is the UV divergence, and this is something that is still not relevant for the current paper that we wrote. So it's not relevant for the real contributions, but this will be of great importance for our next paper, which is on the virtual contributions. Then we have to use UV divergence everywhere to regularize the transverse integration of the momenta. These are some diagrams that are involved as a part of the Trijet cross section. And so we computed everything, and everything can be found in the paper that we wrote. But of course, it's not so, since this project and the result are so, let's call it, an error can occur. So that's why it was important to check some limits to see that everything is correct. And so there are 2 interesting limits to check. The first one is the soft, and the second one is the collinear. And this is what we did. So we took the result for the cross section, and we checked what what we get when for example, one of the partons becoming soft. So we expected that by doing that, we will reproduce the GIMWLK evolution of the leading order result. So, and indeed, this is what we saw by doing that. So there are many simplifications. For example, when we take the Icona limit in the kernel, we get a much simplified version of it. And then as you can see in this slide, for example, you can see the result that we found by taking the Icona limit here. So this is the result. You see it at the bottom of this slide. What you can see here is that you immediately recognize that in the bottom of the slide, this is just the DGLAP evolution of the dipole. Sorry, the BK evolution of the dipole. So this is BK acting on a dipole. And this, the first lines, this is just the leading order result, which I showed you. So you see, you recognize this DGLAP splitting function that was a part of the leading order result. And as you remember, the dipole was the last term in the structure of the in the red box of the leading order. I can give you another good example of what we found that, by taking the soft limit. So here are a different set of diagrams that we checked the Icona limit. And we again saw that you can see the first two lines, they are again part of the leading order result for Dijets. And then in these four last lines, you can see that this is the BK evolution of the first term, which was in the red box of the color structure of the leading order. So the first term was a quadrupole dipole interaction. And this is exactly BK acting on it. So this was about the soft limit, and of course there is another good limit to check is the collinear one. So in the collinear limit, this is the limit which is the separation of two partons becoming arbitrarily large. We expected to find the DGLAP evolution on the initial and the final quark state distribution. So we checked this limit, and for example, what I'm going to show you in the next slide is what we get by this limit for this diagram together with the three at the bottom of the slide. So by combining them together, we found the following thing. And after integration of the last line by using this integral, we can immediately identify that this is exactly DGLAP evolution. So this is the one real step in the DGLAP evolution of the quark distribution inside the proton. And this is exactly what we expected. So we were happy. We got some confidence in our result. And now this is the second part of my talk. This is something that is still ongoing. So this is I'm going to give you some ideas about the virtual contributions. So as I mentioned, so the full cross section can be written as two parts. So the real part and the virtual one. So the real contributions, they can be found by integration of one of the partons of the Trijet. But unfortunately, this trick cannot be used for the virtual contributions. So here we have to compute everything from scratch and without using this trick. At the bottom of the slide, you can see some of the contributions. This is the quark loop contributions. And we gave some names to these contributions. So the contributions in which the shock wave appears at the end. So this is what we call the L diagrams. We are going to sum together all these diagrams. And for these diagrams, we have to use DIMREG to tackle the divergences which are included in the integration over the parton in the loop. And these when they when we combine them together, we managed to get rid of the divergences. And based on our expertise with the real part, we knew that we have to sum together the two diagrams in which the shock wave appear on this quark anti-quark, and on the quark gluon, which appeared before the gluon splitted to quark anti-quark. We call this group of two shockwave insertions. So we compute them together. They always come with a respective minus sign between these two diagrams, in such a way that when these quark and anti-quarks are shrinking, these two diagrams are canceling each other. So that's why it was good to treat them together. So they are always coming together with each other. So, this is the structure. So we compute together all the L diagrams for all the possible contributions, and the S diagrams, we pair them together. So let me give you a more precise example. For the case of the quark anti-quark, we see that we have a term, and then we have its subtraction when the two partons are shrinking. So you remember that for the real case, we had three subtraction terms. Now we have only one. Now the most complicated part of the virtual contributions are of course the L diagrams. And these contributions, they already been calculated before us by Thomas Lappi and Risto Paatinainen, and unfortunately, their calculation was containing some errors, and we knew that because there was a power law divergence in their calculation. And we know that these diagrams, they cannot have something worse than low divergence. And that's why we computed them from scratch once again. And then I'm going to give you some more information about that. Just before I move on with this slide, let me just give you a quick comment that our interest, at least for this project, was the large NC. So some of the contributions that you can see in these slides, we could ignore them because they are suppressed. For example, this one and this one, they are not part of the large NC. But in general, it might be a good, so it's upgradable project. It's possible to add them later on. Let me give you more precise information about how the result looks like. For example, let us pick the case of a gluon loop. So you can see here the result that we found after doing all the regularization procedure. So this is basically after using DIMREG and introducing some sharp cutoff, which you can see here, this lambda. And effectively, this lambda is a parameter which is the lowest value that can be of the longitudinal momentum. So this is something that basically we want to take to 0, but as you can see, if you just taking lambda to 0, you get a divergent result. Fortunately, we managed to show in our result that all those infrared logs, all those divergences are actually canceled when you compute together all the different contributions to the process of quark going to a quark gluon. So you can notice that there are two kinds of divergences. So this log times this log, so this one, and the log square. Now, if you write down the coefficients of these infrared logs for each of the relevant diagrams, then you can see, so I wrote them in this table here. And what you can see is that if you sum up together all the coefficients of the contributions, you get 0 for both the infrared logs. Now, if we take the remaining finite piece of the outgoing state after combining together all the relevant contributions and the cancellation of the infrared logs, we can write down the result by using the same structure as the leading order. But now you can see that we have to introduce some kernel. So this is the only difference from the leading order result. Is now we have some kernel that is encoding the beta function together with the cusp anomalous dimension. And this cusp anomalous dimension is not the regular cusp anomalous dimension that we meet for the case of econal emission. So it's going to somehow depend on the on what we call theta, which is the fraction of the energy of the gluon to its parent quark. And but if we take the econal limit, which means this is the limit that theta goes to 0, if we take this limit, we reproduce the same familiar cusp anomalous dimension that we usually meet in QCD. Now that's basically, we hope to finish with this project within a couple of months. So hopefully this will appear soon on archive. And now the interesting question to ask is what comes next. So so we have a few interesting ideas to explore once this project will be finished. And of course, there is one thing that we, I mean, if we want to systematically compute the cross section, we have to replace the incoming quark with a gluon. So this is known as the gluon channel, and this is something that we must compute if we want to consistently make a check with the DGLAP. I mean, if we want to absorb all the divergences to DGLAP in a correct manner, we have to include also these diagrams. So this is something that we want to keep in mind, maybe as a future project. Another thing is that we want to explore the possibility of making a transition from PA collisions to EA collisions. So as you can see, so in order to compute the relevant outgoing state for DIS, we have to dress this outgoing state at leading order. So up to here is, so photon splitting to a quark, anti-quark is the outgoing state at leading order. And we want to check the possibility to dress this wave function with what we found for the evolution of the quark. And by doing that, we will be able to arrive at the NLO outgoing state. And then we can find some interesting cross sections, as you can see in the bottom of the slide. So this is another thing that we check as a good idea for future projects. Now let me give you some summary of my talk. So we managed to compute the full outgoing state, and from this outgoing state we managed to deduce the cross section for Dijet production. We managed to show that the result is free of divergences. The first one is the short divergence. So we managed to show that there are always a pair of diagrams which are combined together in such a way that when there is a divergence which is occurring, so in this region that one of the divergences, so one of the diagrams diverge, there will be another diagram which is canceling this divergence. We managed to show that the result in the equinal limit, the result that we found in the equinal limit is reproducing the action of B-JIMWLK on the leading order result that Cyril found. And we managed also to get a full match with DGLAP evolution in the collinear limit. And the last thing is that the L diagrams, we managed to show that they reproduce the correct beta function in the cusp anomalous dimension, and all the infrared logs shown to disappear once we combine everything together. So this is everything that I wanted to say, basically.
Okay, thank you very much. So, somebody has any question? I see no questions in the chat.
I have a question.
Okay, go on, please.
Jair, so no, this is a very nice result, but then when you're going to calculate the observable, you have to include expressions for your dipole and your quadrupole. So what will be the correct thing? You will need to use these correlators. You need an evolution, right? You need to do BK or B-JIMWLK, and you will have to do it at leading order or at next to leading order. What is the consistent thing to do?
Not sure I understand you. So the dipole and the quadrupole, they are defined in the usual way. So they are defined in leading order, and we don't need to change this definition.
I mean, you don't have to change the definition, but they depend on the rapidity, right? And this is always the question with this next to leading order calculation is what is at what rapidity do you have to evaluate your correlators, and what is the evolution that you use to calculate the rapidity dependence of your correlators?
Okay, so there is, yeah, I understand what you're saying. So there is a like expectation value that you have to indeed compute these dipole and quadrupole, but I mean, this is something that is not dependent on the result. I mean, if you are doing it on leading order or next to leading order. So, I mean, you are doing average values on these expectation values, I mean, it doesn't matter if you compute leading order or next to leading order in that sense. I cannot really understand.
Yeah, I don't recall the details exactly, but I remember a few years ago when the calculations for the single hadron at next to leading order, for example, not the one you have the double differential, right? But a few years back when the discussion was about the single inclusive, there was
Yes,
always this subtlety about what is the rapidity that you use to evaluate your correlators, because that's something that you need to fix at some point to actually compare to if at some point you want to compare to data, right? You have to evaluate.
Yeah, if you want to compare to, I agree. If you want to compare to data, then you have to do it consistently. That's true, but I mean the result. In that sense, you write it down as I wrote it, and then you still have to evaluate it in a correct way. I agree, but I mean, it doesn't mean that, we want to go to this part in what we are doing. Anyway, Fabio, so the idea is very similar to single inclusive. So we actually used the idea in your paper, so we have to combine together some of the terms in such a way that we get the plus prescription at the end in order to show that indeed there is no divergence left.
Yes,
so
no,
it's
no,
just
that
kind
I
of
understand. Yes, it's very good. Yeah.
Okay, any more questions? Let's see. Well, actually, I have one. So well, I didn't notice until you mentioned that you always start with a quark. So you always assume that the parent quark, parent, yes, just for curiosity. So is there a way to experimentally distinguish the two situations if the parent was a quark or a gluon?
Yeah.
Okay.
Yes. So we are. If you are interested in the very small region, so a very low x, then the quark is the dominant part. So if you look on the PDF of the quark and the gluon, you see that there is a region in which the PDF of the quark is the most dominant one.
Okay.
And then you can use it and to explore this. But in general, if you want to explore some regions in which X is not so small, then you must include the gluon contributions, and then they can become also dominant. So I agree that these are some important contributions. In general, they cannot be neglected, but you know, it's a good start. We cannot do everything from the beginning.
Yes, of course.
It's lots of effort, but it's good to keep in mind that this is not everything. I mean, so in general, we have to add together also the other channel, so the gluon channel.
Okay. Okay. Very good. Okay. Thank you. So I don't see any more questions, so I think we can thank Jair again.
Okay, thank you so much.
Thanks, Jair.
Okay, and thank you very much, and goodbye.
Thank you very much.
Goodbye.
Bye.